Hi all, let's continue with the next topic of Unit 3, the sign magnitude addition and subtraction. So in the previous lecture we have already started with the sign magnitude addition and subtraction, where we have seen a tabular column which explains you all the four combinations of addition operation and subtraction operation, and we have also seen the examples. So in this lecture today we are going to discuss about the hardware implementation of sign magnitude addition and subtraction along with its flowchart. So in the previous class this table has been already discussed, where we come across the four different operands, combination of operands for addition and as well as subtraction. So now we'll discuss about its hardware implementation. How the hardware of your computer is internally organized in such a way that it can perform this sign magnitude addition and subtraction operations. So if you look at the hardware, it basically contains two registers A and B, which are used to store your operands. So operands in the sense they store only the magnitude part of your operands. In case of a sign magnitude data, we know that it contains an sign bit as well as a magnitude part. So the registers A and B holds the magnitude part of the two operands A and B, whereas the AS and BS are used to store the sign bits of the operands A and B. Okay. Apart from that, we have a complementer and a parallel adder. So the parallel adder is used to perform an addition operation on the contents of two registers A and B, and we also have E flip flop, which we call it as an extended flip flop, that is used to store your carry bit out of your addition operation. After performing an addition operation on the contents of two registers A and B, if there is any output carry out of the particular addition operation, that is stored into a extended flip flop E. And we have one more flip flop called as overflow flip flop. So AVF stands for add overflow flip flop. This is used to store the overflow. If there is any overflow out of your addition operation, then this overflow, it is stored in the overflow flip flop. And then we have a complementer. So this complementer takes an input, the mode control bit. So the mode control bit can be set to either 0 or 1. The result of the operation, addition operation, is stored into either the one of the source register A, or it can be transferred to a third register. And similarly, the sign can be stored in a AS register. So first we require a parallel adder that need to perform a micro operation A plus B. Secondly, we need a comparator circuit. So, in case of this table, if you observe, if the operands are one is positive and one is negative, if first is negative and the second is positive, in this case we have to compare the magnitudes. So, for that we need a comparator to be available in our hardware. So, second comparator circuit is needed in order to establish if A is less than B, or A is greater than B, or A is equal to B. And finally, a subtractor circuit is needed to perform the micro operation A minus B and B minus A. So based on these requirements, the hardware implementation has been done, which contains two registers A and B that are used to store the magnitude part of your data, and the flip-flops AS and BS, which are used to store the sign bit. So here the subtraction operation is done by adding A to the 2's complement of B. So if I have to perform a subtraction operation of A minus B, then I have to add A to the minus B can be represented as 2's complement of B. In that way, I can perform A minus B. So if you see here, there is no subtractor internally present in the hardware. Through addition, using a complementer, through addition itself, the subtraction operation is being done. So the output is transferred to the, if there is any carry out of an addition, the carry is transferred to the E flip flop. Otherwise, the E flip flop will be 0, and the result sum. S represents the sum. The sum is loaded again back into the A register, one of the source operand. So here there is one more bit called mode bit. So when the mode bit M is equal to 0, the output of the bit, it performs an addition operation. So how do you determine, say I have a content of one operand present in A and one operand present in B. How does the hardware know which operation to perform, whether to perform an subtraction A minus B or addition A plus B? So that is done based on the mode control bit. So whenever this mode bit is set to 1, then the output of B register is transferred to the parallel adder. The input carry is 0. So the same mode bit is given as a input carry to the parallel adder along with the contents of B register, and it takes the contents of A register and it performs addition operation of A plus B. So now so here it becomes A contents of A register plus input carry 0 plus contents of B register. So A plus 0 plus B, it becomes A plus B. So that is how an addition operation will be performed. Coming to a mode bit, when the mode bit is set to 1. So when the mode bit is set to 1, then the complementer will perform the ones complement of B is applied to the adder and the input carry is 1. So the ones complement will be, so if I have to perform A minus B, I can write it as A plus 2's complement of B. For 2's complement, I have to perform 1's complement plus 1. So whenever the mode bit is 1, the complementer will perform the 1's complement of B, and the 1 input carry 1 is added to it along with the contents of register A. So it becomes A plus 1 plus B complement. B complement 1 plus B complement is nothing but minus B. So it performs A minus, that is equal to A minus B. So this is how the hardware performs the addition and subtraction operation with the help of the complementer and a parallel adder. So the same is explained here. A and B are two registers that holds the magnitudes. So the hardware implementation consists of registers A and B and the sign flip-flops AS and BS. Subtraction is done by adding A to the 2's complement of B. The output carry it will be transferred to the E flip-flop. And add overflow flip-flop holds the overflow bit when A and B are added. Okay. The addition A plus B is done through a parallel adder and the sum is transferred to A register. So what is the difference between a carry and an overflow? So let us take an example. Say I want to add two binary numbers 10 and 9. So if you are performing an addition operation, when the result of that particular addition operation cannot be represented in the range of bits. Say I am adding 10 with 9. So the binary equivalent of 10 I am representing in 4 bits. So it is 1010. And I am adding 9 to it, which is 1001, the binary representation. So when you are adding these two numbers, and what is the range of numbers that you can represent in 4-bit representation? It ranges from 0000, 0001, 0010, 0011, and so on. You can represent till 1111. So the range is from 0000 to 1111. So here if you see this range, this is 0, and if you see this 15. So you can represent the numbers only from 0 to 15. So what would be my result? 10 plus 9, it will give me 19. So say for example, when I am adding this 0 plus 1, 1, 1 plus 0, 1, 0, 1 plus 1, it gives me 1, 0, 1, 0. So this 1 is nothing but my output carry. So we mean to say that when you are getting an output carry bit as 1, it means that your result cannot fit in this particular 4 bits. You are moving out of the range. So we call this as a overflow. So whenever you have an output carry, then your overflow bit will be set to 1. So for example, if you don't have a carry here, if you then your carry bit will be 0, then there will be no overflow. So when the result of your operation is going beyond the range that you can represent, then we call it as an overflow. That happens only in case of an addition operation. It will not occur in case of subtraction operation. Okay. So in case of a sign magnitude addition and subtraction operation flowchart, so we have a subtraction on one end and addition on other end. So here we'll start with an addition operation. As we know, we have four possible combinations of addition, either two positive values or two negative values. The first operand is negative and second operand is positive, and the first operand is positive and the second operand is negative for all the combinations. So I have an addition operation where my augment is stored in A and addend is stored in B. So I have to first check the signs of A and B. So AS and BS represents the signs where A and B represents the magnitudes. The two signs A and B are compared using an exclusive OR operation. In both the signs, in the subtraction side also, the minuend will be in A and subtrahend will be in B, and the signs of both minuend and subtrahend will be stored in AS and BS respectively. So in both the sides, first we have to before performing an addition or subtraction operation, we need to check the signs of the both operands A and B. So that is done by performing an exclusive OR operation on the sign bits AS XOR BS. So if the output of an exclusive OR operation is 0, so it means when will be it will be 0 on the addition side. If the signs, both the signs are either positive or both the signs are negative, then this output will be 0, right? So in that case, we need to add the magnitudes. So similarly, if the signs are different, then we need to perform a subtraction operation. So then it goes to the subtraction side. Similarly, at the subtraction, if the signs of both the operands are different, then we need to perform an addition of the magnitudes. If the signs of both the operands are same, then you need to perform the subtraction operation. So for subtraction operation, different signs indicate that magnitudes must be added. The magnitudes are added with a micro operation. EA implies A plus B. So when you are adding the magnitudes, you are performing the addition of magnitudes EA, where E stores your carry bit and A stores your result of your sum. Okay, and if there is a carry out of this addition, then that is nothing but your overflow, that is stored in your, that is transferred to your overflow flip flop. Both the signs are equal, not same, then you perform an addition. If both the signs are equal, then you perform a subtraction. At the addition side, it is a reverse. If both the signs are equal, you perform an addition. If both signs are different, then you perform a subtraction operation. Coming to a subtraction operation, how do you perform a subtraction? You are performing A plus B complement plus 1, which is nothing but A minus B. So you are first performing A minus B. Since you don't have an overflow condition in case of a subtraction operation, this is just an add overflow. So it will be clear to 0. There is no possibility of overflow here. So after performing a subtraction operation, we are checking the EA stores the E stores the carry and EA stores the output of your result of your subtraction operation. So next, after performing this addition, we are checking the value of E flip-flop, which is a carry flip-flop. If E is equal to 1, then it indicates that A is greater than B or A is equal to B. So if A is greater than or equal to B, then in the subtraction table, we have to check if A is greater than B or A is less than B or A is equal to B, right? So based on E, we are going to decide whether A is less than B or A is greater than B or A is equal to B. If E contains a value 1, it indicates that A is either greater than B or either equal to B. So when if E is equal to 1, again we are going to check the value of A. So if A contains 0, so if A and B are equal, then the result which is stored in A, what is stored in A now? Now it contains the result of A minus B. So whatever is stored in A, if it is 0, if both the operands are equal, it gives a result of 0. So if it is 0, we have to make it a positive 0. So for that, we are making the sign bit of the particular result as 0. So if in the case if A is a non-zero value, if A is not equal to B, in that case we'll get a non-zero value in the register A, the result register A. So in that case we need not have to do anything, that is your actual result. Say for example, in this case, if E flip-flop contains a value or carry flag contains a 0, it indicates that A is less than B. So when A is less than B, you have to perform a complement of A 2's complement. Whatever is your result, that is not your actual result. You have to perform a 2's complement of your result to get your actual result. So for performing a 2's complement, I have to first perform 1's complement. So A bar implies 1's complement. So whatever is stored in whatever result is stored in A, I am performing a 1's complement of the result and adding it to 1. Now this A contains the 1's complement. So for that 1's complement result, I am adding it to 1 so that I get the actual result. So when after performing a subtraction operation, you need to check the carry which is stored in a E flip flop. That based on the carry, you are going to determine if A is less than B or A is greater than B or A is equal to B. If E is equal to 1, it indicates that A can be either greater than B or less than equal to B. How do you determine if it is greater than B or equal to B? If both A and B are equal, then obviously when you are performing a subtraction, the result will be 0. So you are checking with the result. What is the content of register A? If it contains 0, it means A is equal to B. Then the result will be 0. So you are making your sign of your result as 0, positive, because 0 is always a positive sign. In case if the content of the resultant register A contains a non-zero value, it indicates A is greater than B, and whatever subtraction we have performed, that is correct. Whatever is stored in your A and AS flip-flops, A register and AS flip-flop, that is your actual result. On the other side, if E is equal to 0, it means that A is less than B. So when A is less than B, then you can whatever you cannot subtract larger number from a smaller number. So whatever result you got here in your stored in your register A, that is not your actual result. That is your 2's complement of your actual result. So you have to perform 2's complement of this result to get your actual result. So I am performing the 1's complement first. A bar is nothing but the 1's complement and adding 1 to it to get the actual 2's complement. And what is your sign bit? The sign bit is nothing but the complement of sign bit of the minuend A. So that is how a subtraction operation is performed using this flowchart. So addition is simple. You are just adding the contents of A and B register. The result is stored in E and A, where E contains a carry, A contains a result. So whatever is in E, if there is a carry, that is stored in that is transferred to the overflow flip-flop. That is considered as your overflow. So this is the flowchart of addition and subtraction of your sign magnitude data. So these two signs A and B are compared by exclusive OR gate. If the output of XOR is 0, the signs are identical. If it is 1, the signs of different. For an AND operation, the identical signs, if the signs are identical, you are performing an addition. For a subtraction operation, if the signs are different, then you are performing an addition. So the magnitudes are added with a micro operation. A implies A plus B. So where E contains your carry and 8 contains your result. So then you are going to check the carry in E after the subtraction constitutes an overflow if it is 1. So the value of E will be now, if E contains 1, it means there is a overflow, and that is transferred to the overflow flip-flop, add overflow flip-flop. And when in case of subtraction, the two magnitudes are subtracted if the signs are different for add operation. And in case of if they are identical, then you are going to subtract in case of subtraction operation. So the magnitudes will be subtracted by adding A to the 2's complement of B. So in this case of subtraction, there is no overflow cannot occur. So you are making your overflow clear to 0. Next, in the case of subtraction, we are checking the value of E flip-flop. So this is your E flip-flop. You are checking the value in E flip-flop. So if E is equal to 1, it indicates if it can be either A is greater than B or equal to B. And the number whichever in A is the correct result. Whether it is greater than A or equal to B, whatever is in A, that is your correct result. So if E is equal to 0, then the condition is A less than B. And the number whichever is stored in your result register A is taken 2's complement. You have to take the 2's complement of it, which will be your correct result only after taking the 2's complement. So if the sign of the result is same as the sign of A, no change in AS is required. Whenever your A is less than B, the sign of the result will be the complement sign of A. So finally, the results will be stored in, whatever is the case, the output of your addition or subtraction operations will be stored in one of the source register A, and its sign of the result will be stored in your flip-flop AS. This is how you perform addition and subtraction operations. Thank you.